Hi there. Welcome to this meeting of the Warren Astronomical Society. We are live and hybrid at Cranbrook Institute of Science. I'm your president, Bob Tremblay. Let's see, our next Cranbrook meeting is September 8th, not the 1st, which is Labor Day. So we're not going to be here Labor Day. So week after that. So tonight our short talk will be how to take the best Milky Way pictures ever by Adrian Bradley. And our main talk will be the DART mission by Nancy Chabot. I believe that's how her name is pronounced. She was a guest for the Vatican Observatory Foundation's full moon meetup a while back, and she was fantastic, and I recommended her to Dale. I was quite surprised when he announced at Macomb that she was going to be talking. I'm like, cool, she's really good. So do we have any first-time attendees tonight? We do. Hi. Spotlight on you. How'd you hear about us? Pardon me? How'd you hear about us? Yeah. Meetup? Cool. Well, this is the place to be. Hope you enjoy the show. The internet. Imagine that. So we have an observatory at Walcott Mill Metro Park, which is 29-mile road between North and Romeo Plank. We have a free open house every fourth Saturday of the month, and we are doing a Perseids party on the 9th, opening it up, and it's going to be a full moon that night. So you're probably not going to see a lot of meteors, but we'll be observing anyway. So we meet on the third Thursday at Macomb Community College South Campus, and we have a whole bunch of people that talk about astronomy and space science, and will come to wherever you are and set up telescopes for free, and schools and stuff. So yeah, we're a really cool group. Yeah, and libraries. I need to do more libraries. I need to do a lot more libraries. Okay, you can join or renew your membership here with David. Note that anyone joining for the first time is paid through December 2026, so that's cool. Members get a name badge, and we just passed something probably has to be entered into the bylaws. New board members will get their membership paid for. Speaking of board members, we are having elections in November, and some of us are being term limited out, and we're going to need some new officers. So if you'd like to be an officer for this fine organization, get with us at the snack break. WASP wearables are available, and Mark Kezier, I know he's here somewhere. There is Mark Kezier. You can find what's available in our newsletter. We have t-shirts and sweatshirts and a whole bunch of stuff. WASP stickers are available down here, David. They're great for the back of this or the back of this. Astronomy at the Beach is the largest free astronomy event in Michigan, September 26th and 22nd. 26th and 7th, Island Lake State Park, west of here. We'll have a table under the club tent. Brother Guy Consolmagno, the Vatican Observatory Foundation, has asked me to help him at the Vatican Observatory Foundation's table. He wants to be right next to us, so I'm going to be tag teaming the two tables. So if we can have a couple members at our table at the event, that would be awesome. GLAC is the Great Lakes Association of Astronomy Club. They put Astronomy at the Beach on. They meet every second Tuesday of the month. If you're interested in planning astronomy at the beach, they could use your help. GLAC, pardon me? Online. You don't have to go anywhere. You did have to go somewhere before COVID. Not anymore.
To be out to breathe in. So against that, even though our temperatures would get where I could say to
Thank you. Okay, GLAC is like 7 astronomy clubs, and they'd be interested. So some clubs would be interested in having other members from other clubs give lectures at their club. So if you've given a lecture here, you might want to give a lecture to the other clubs, or vice versa. So that's a good thing. Okay, so officer reports. My wife and I are celebrating our 41st anniversary today. We got to spend it with my granddaughter over, so that was even more awesome. Let's see, are we what?
Very hard to follow. Loves the fact that happened.
Okay, so I can't see what's going on there. Astrophoto calendars, we need your picks. We do an astrophoto calendar every year. So if you're interested in if you've got a really cool picture that you've taken and you'd like to see it in our calendar, send it to publications@warrenastro.org. Dale, first Vice President, Dale Parton.
Just to say what I always say, I need presentations, you guys. Even if you're not used to doing that, talk to me. Let me at the break, or if you're online, send me a message. It can be a short one, a long one, but we want to hear from you guys. So let me know if you got some. Thanks.
I mean, I'm glad that Adrian's doing something on the Milky Way, because a gentleman at our last Cranbrook meeting, when Adrian mentioned the Milky Way, said, "What's the Milky Way?" So this leads into the light pollution page that I just published on the Vatican Observatory Foundation site, and I'm going to be taking some of that content and putting it on our site. So, Riyadh, what is going on at the observatory?
Yes, hi. Hello, everyone. We had our meeting, the open house on the 26th last month. It was kind of cloudy, but we had about 25 or so scouts that called Bob Berta to come out to the observatory, and he came out and he and I gave them a talk. They enjoyed that a lot, and we described the telescope for them and different things that we discussed about astronomy. And then, unfortunately, of course, because the cloudy skies kind of stayed the same way towards the end, we closed the observatory while it was still cloudy, about a couple of 2.5 hours later. Next open house is going to be this coming Saturday, August 9th, for the Perseid meteor shower. So try to come out there around sunset or so. I'll try to be there about 7:30. Hopefully we'll have clear skies, we'll see. And then our open house and the picnic is August 23rd. The next thing I want to say is for September, because of on September 27 is our open house. It's not going to be canceled. I'll still be there, even though we have astronomy at the beach. I'll be helping out on Friday the 26th, but I'll be at Stargate on the 27th. That's all I have right now. Thank you.
All right, thanks, Riyadh. And yes, our picnic is the 23rd, so thank you for mentioning that. David, what's going on with the Treasury? Hopefully we're going to fix that.
Okay, so Treasury, we have in our checking account $22,451. We have a balance on our credit card of $137, and that's from that stuff. That's for astronomy at the beach. PayPal, we have $342. And also I'd like to read to you a letter that we got from Cranbrook. So this is it's addressed to me because I sent the check. But it says, I wanted to extend my thanks to the Warren Astronomical Society for your generous gift to the Michael Stafford Freshwater Forum Fund. Your support helps carry forward Dr. Mike Stafford's enduring legacy while powering some of the Institute's most impactful environmental education initiatives. The Freshwater Forum is the heart of our mission to inspire future generations to become stewards of Michigan's precious water resources. With your contribution, we are able to continue offering dynamic programs like Water on the Go, which brings environmental learning to K-12 students across the state. Your support also helps sustain important community events such as Rouge River Water Festival, the Great Lakes Effect Planetarium Show, and all the Freshwater Forum has impacted over 500,000 Michiganders since its creation, thanks to supporters like you. Thanks to your generosity, we can ensure that these vital programs remain accessible and continue to inspire the next generation of environmental leaders. We're deeply grateful for your partnership in this important work. Thanks again for your support. Your commitment is greatly appreciated. So if you ever wondered why you want to join an astronomy program, here's your answer.
All right, thank you, David. All right, Charlie, are you online? No, he's, okay. Jeff, what's going on with outreach? A lot's going on with outreach.
I don't know, people keep doing stuff and they don't tell me about it, so it doesn't get in the loss. Oh, look at that. Yeah, so imagine this, and then this, and then a TV, and then Bob.
With my computer.
Stuff, and then you go out to the field and there's all that. Oh, man. Take that Ford.
Take that Ford Club, yeah.
Hopefully they haven't gotten wind of this and. I don't know, maybe I'll just throw this in the dryer, so that I was gonna ask Tina if she had a steamer. I knew you would.
Oh my God.
Okay, outreach. Jennifer Dye in the back, Detroit Public Library System, they're gearing up their, what do you call it, summer, fall? Okay. So we're starting it again. It's typically the fourth Tuesday, but not set in stone if there's scheduling issues. So again, if you have a presentation and you've already given it to the club, you gotta go on the circuit. So I'm giving my Apollo talk there in September, so you can't have that one.
Yeah, I know.
Then astronomy at the beach, I sent out an email to many of you earlier today. Some people have still not responded to any of my emails. But I'm gonna get with you individually. If you're like, what email is he talking about? I wanted to volunteer at astronomy at the beach. Talk to me, I will get you on that list. I still need all kinds of. I really need someone to run a small scope. Think I have just about everything else covered. It'd be nice to have like one more.
Still,
I've-
handle a mount that can take 11 pounds and has a 50 mount, I can easily do that.
Yeah, but you're not gonna be there Saturday.
You're right, I understand, it's in our guide.
And I think we don't have the tables covered completely. Cause Bob has to also go to the Vatican table. And then some other people are not available both nights, if I'm remembering correctly. So if you'd also just like to hang out at the table for an hour or
Just
two.
hang out at the table, that's all, that'd be great.
You guys know when we meet and where we are. That's most of, they're not asking you how the space shuttle works. They just want to know about the club.
Well, yeah.
They might ask you how the space shuttle works. I think that's it. Am I missing something?
One thing we probably could use is a couple people just to be gophers.
I got
People,
one.
people that just walk. The telescopes are going to have lines, and it would be nice to have people talking with them. This is what we're viewing, you know, just chat them up while they stand in line for God knows how long.
But we're also gonna do some things. I'm trying to have dedicated targets so that when you're in the WAS red circle zone, each telescope is on a different target, and so people aren't gonna stand in line, get to the front and go, Saturn, I already saw Saturn.
And I waited 2 hours for it.
Well, this is a different Saturn, so.
Rope into that area.
We got plenty, we got 150 feet of this, so we can do as many as you can find me.
Okay, I'm
We-
gonna start shaking down.
We can have 10.
Okay.
Yeah, there's no limit. It's not like, oh, we've got our 5. No.
I've already invited someone, but
Okay,
not part of our group, but part of the association.
okay, and then picnic. Picnic's coming up,
23rd.
23rd. Be there. There's a swap meet.
You got any telescopes you want to sell? Got any telescopes you want to buy? Be
Club-
there.
Club telescopes for sale.
Want to show off your new solar scope?
That's all.
All right. Thanks, Jeff. All right, so. Either, so
On the weekend of astronomy at the beach,
So that we're meeting on the Tuesday following that. And Jeff is giving his presentation on the moon is not forward.
Oh, yes. What day, do you have the date for that?
I do, I've got my.
It's not for a little bit, cause it's in October, I wanna say.
Yeah, observe the moon. Yeah,
Yeah.
October second week-ish.
Okay.
But the library closes right when the moon is due to visit. So I'm doing it
Yes.
on a Saturday.
So if you've not seen my Moon is Not Boring talk, you can have the Detroit Public Library.
That's the game time.
All right, so newsletter. Our newsletter is online. Dale got that up, what, yesterday? No, 2 days, on the first. So our award-winning newsletter and our award-winning newsletter editor. Let's see, if you need to contact the board for any reason, you can email us at board@warrenastro.org. Let's see. Okay, David Levy's not here. All right, so astronomy news. The third interstellar comet, 3I Atlas, was discovered on July 1st. It is now showing a coma. And with the Vera Rubin telescope being online now, it's likely that we're going to discover a boatload of these interstellar type objects. And of course, looking through this, I saw another Harvard scientist suggest what looks like a comet might be alien technology. Found out it's that same Harvard scientist that's doing this stuff. And says one report I saw said, this scientist is well known for pushing bold and often polarizing theories about extraterrestrial life. So right now it is, let's see, can I put this over here? Right now, that's it. Oops, there we go. That's its orbit. And of course, I'm not sharing it with the online group, but it's in the asteroid belt. It's coming. It's
What if then indicates technology to this person? Not stupidity.
yes, exactly.
Just that you can say that.
Yeah.
And his love, it's the difference is he's Dr. Mitchell.
So I saw an interesting article that I thought Dale would be interested in. Cosmic rays could support life just under the ice. Now, if you know about cosmic rays, they're all over the place and they're very energetic. And the report says a team of researchers looked at the process of radiolysis, I think it is, which occurs when cosmic rays slam into water or ice. The high-speed particles break water molecules apart, which releases electrons, and some bacteria on Earth use those for energy. Could the same thing happen to possible life forms on icy worlds in the outer solar system? Probably. So we have 1,000,004 asteroids, up several thousand from last meeting. We have 38,009 near-Earth objects, up 150. Exoplanets, we're up a few. I'm a little disappointed this time, but we're getting real close to 6,000 confirmed. NASA, the Exoplanet Archive, added 27 new spectra to their atmospheric spectroscopy table, which brings the total to 1,000 transmission, eclipse, emission, and direct imaging spectra for exoplanets. So that's really cool. This week's exciting news is planet TWA-7b, a Saturn mass object directly imaged by the James Webb Space Telescope. If confirmed, it would be the first exoplanet discovered by the James Webb using direct imaging, and is also the lightest planet ever seen with this technique outside our solar system. So that's pretty cool. Special interest group. The predicted nova of T Corona Borealis still has not occurred, and the sidebar on spaceweather.com is just showing that it's actually down again. I think I'm just going to stop reporting on that. It'll just report when it happens, because we've been waiting on that for what, coming up on a year now. So we got some sunspots. Let's bring this over here, and I will be sharing it with our yeah, there's a busy sun. Let's see, can I share that? Nope. Yeah, I'm working on the second screen's a pain. There we go. All right, share it. All right, so there's our sunspots. We got a lot of them. All right, let's Stop the share. All right. Max, please. All right. If you're on Facebook, check out CME Alerts and the Solar Activity Group. They've got amateur astronomers posting pictures on there, which are just amazing. Every time I see them, I always think, you know, the solar astronomers from the mid 1800s would be crying if they saw what amateurs are doing today. So if anyone wants to start a special interest group, like you're into radio astronomy or computers, technology, education, light pollution, which I'm probably going to be doing, and podcasting, just let us know. Go ahead and do it and start reporting on it. So do we have any observing reports or astrophotos? I know you have one.
Smoke.
Yeah, Dale messaged me and says, the moon, if you looked at the moon, it doesn't look quite right. I'm like, huh? Well, I go outside and there's the first quarter moon. I'm like, what is going on? It really looked weird. So I'm wondering what that's going to do for Saturday. But yeah, so we got smoke and it's making the sky look really, really awful. What do you got? What? New update? If our listening audience didn't hear that, the S-Star S50 has a software update that has AI denoiser.
Great pictures.
You know what? After my wife saw something on the C-Star, she says, "Why don't you have one of those?" I'm like, I don't know. I'm waiting. I want to get the $1,600 solar scope first.
Yes, there was a discussion on Friday nights about that. Nobody can download it because it's so crowded. They can't get on the website.
It's crashing their site. You know, I've got a conspiracy theory. Right? The C-Star is just stored data. It's not actually showing anything. It's just painting a picture. There's my conspiracy theory. How do you prove that the C-Star is actually seeing something?
You could look through a telescope and verify.
Yeah, but your smoke's making your contrast worse now, so.
Yeah, well, I suppose if you set up a C-Star inside a house and it starts painting a nebula, you'll know, but
Yeah.
I do want to get one of those. All right, so any other observing reports? If not, Adrian, you're up. Let's get your presentation up and shared here. Best Milky Way. Let's see. From beginning. And what's there? And I gotta share that now.
Good.
So not the share I want.
That's hard. One. Oh yeah, you got it fired up on screen one. So
Screen one,
click that
okay.
And share, it should show up. So now it's being shared out.
Okay, you got. That's not being, what is that?
That's
That is
the other
not it.
side. So if you put screen two, then you can move it. We'll be able to move the presentation out to that screen.
Best Milky Way other.
All right, so
This, I'm gonna duplicate,
okay.
so I'm not doing two
Yeah,
different
if we
screens,
started, it would probably
Yeah.
fire it up.
and that's just too confusing. Keep, all right, so there we go.
There we go. And then we can blow that up. There we go. Now I'll just go through each slide. Or I start the slideshow, then I can click, which would be better. I'll do that.
Share.
After.
Now, where is it? Tech is failing me tonight. Where is it?
What are you looking for?
I'm looking for the share button on Zoom.
Go down to
Not that.
Zoom, click there. And find the Zoom meeting again.
That?
Yep.
That's.
No, that's the wrong
That
share.
PowerPoint share.
Yeah. So when you click on Zoom, go to the. We'll do that in a minute.
Where's the?
There's the Zoom. It's
Where?
disappeared.
Where is the meeting?
The meeting has disappeared.
Oh my God. I don't need that. There it is.
Okay, it went real small.
Yeah, okay.
Okay.
So now I got to share PowerPoint.
All right, now we're.
There you go.
Sorry, not sharing.
Can you see that, Dale?
Oh, yeah.
All right, move him.
Oh,
How do I get help? Good
job.
Lord. There we go. And now I'm getting out of here.
all right. I gotta wait right past on this broke.
But you fix that.
Oh, God.
Okay, well, tonight our short presentation is going to be given by Adrian Bradley. His specialty is wide angle landscape astrophotography, where you can see stuff on the land, on the ground, and stuff in the sky, especially Milky Way photography. I would say the way he composes his pictures is essentially art. And he enjoys doing this so he can share his love of astronomy with people like us. He's involved with several astronomy organizations, including the Royal Astronomical Society of Canada, Explorer Alliance. I don't even know what that is.
The Explorer Scientific's group of VIPs.
The Astronomical League, the University Lowbrow Astronomers, GLAC, and of course, he's been a member of this August Society for 5 years now. He has recently published 3 articles, I presume with photos, in Astronomy Magazine. And tonight, he's going to share his secret sauce, how to take the best Milky Way pictures ever.
All right. So. Okay, so first, that has to move. Yeah, and it will switch as soon as I hit start the slideshow. Which I will do. Where is your slideshow? Right there, I see it. Slideshow. From the beginning. All right. So this is a presentation on how to take the best Milky Way photography photos ever. And I set it up like this because whenever you put a clickbaity title like that, everyone comes out and says, really? How do you do it? Well, so let's get into what it might mean to take a best photo of the Milky Way. Now, I come from a background of being an astronomer, so learning the night sky was more important. You can take beautiful pictures and all you do is photography, but those paths can be very divergent. So, all of this stuff over here that I put is usually what is going to be assumed, especially if you go on the internet and listen. You're going to need all of these things: expensive DSLRs, mirrorless cameras, intervalometer. An intervalometer helps you take multiple pictures. And in some cases, that does become helpful. A computer to process everything, image editing software, being a naturally great photographer, I disagree. Now, all of this can be true the more you do it. You want a camera that's, can help you achieve good focus, control light and everything else.
Let me get the lighting down.
Okay, go ahead. Oops, say that again. To see the Milky Way? Yeah, well, depends. There's an image I didn't include, but there are some places where you can have a quarter moon out and still see the Milky Way in all its glory. But we'll get to that. That's actually a part of the secret sauce. So let's go and tell you why it's not true. Now you see this Milky Way image behind us. This is a picture taken by a smartphone. Brian Autumn, he has a 3.5-year-old smartphone and he aimed it at the sky. So you're looking at that and go, my smartphone can do that? Well, there's a reason your smartphone can do it, and it may not do it so well here in Michigan. So what we're doing is that secret sauce that Dale talked about, we're going to get to why. And hopefully none of you are disappointed when I tell you why you can use a smartphone to take a Milky Way photo like this. We're going to get to it. So what about the settings that's worked so great? It gets published like this. I'll always be proud of this picture for a couple reasons. Other than the fact that it was published in June 2024 Astronomy Magazine. This is a Milky Way photo. Who here knows why this is a Milky Way photo? Go. Yes, a oft overlooked Milky Way photo covers branches of the Milky Way we can see other than that great big core. So this still counts. Now, where I was, you could not only see the zodiacal light crossing with that winter branch, you could see that winter branch pretty easily. So that's another hint. It's places where you can see the winter branch. Go to Lake Hudson in winter and see if you can see that winter branch. But there's a huge part of getting a great Milky Way photo has to do with what you can see. And so if the goal is to get published and take great works, you might do things like try and catch a part of the Milky Way, this Cassiopeia Perseus branch. There's the Andromeda Galaxy. Somewhere down there should be in 33 as well. And you've got the kind of the picket fence aurora going with it. That ought to be a great shot. But truth is, a great Milky Way photo is all in your mind. It's all about what it is you're trying to capture. And if you think it's a great photo, well, okay. The problem comes in with what you're going to do with your Milky Way photo and what it is you are presenting. So establish a purpose. Lesson one, establish a purpose for the Milky Way images that you shoot, and they will become great in their own right because they won't just look like your typical, put some really cool foreground in the front, have the Milky Way going across it, and bam, that great Milky Way shot. Now think about what it is you want to do with your images or how you want to take them. All right, now why can't I see the mouse? Okay. The mouse is breaking again, so I'll just use this. So what does it take to take a good Milky Way photo? Here is an example, and I put some technical jargon for those. 2-image composite. That means I put a ground together in the sky. A longer tracking of the sky. That gets into a little bit of the old school astrophotography where you're tracking the sky. So you end up needing a tracker for that. 2 minutes untracked. You can read that if you understand it. You're well on your way to having a technique to get images from just about anywhere. This is a good technique to use to get images. You're not going to get them to look like that. Again, there's a reason that we have all of this detail in this location. Or take a single shot. Location, location. So out in Black Mesa, Oklahoma, there's Allosaurus tracks, and this is the nightfall is coming, but we are just on the edge of nautical twilight and astronomical twilight, and the Milky Way is still so visible. A 13-second image on a stationary tripod can pick it up. Now, is there some processing? Yes, to pull out some of the features that you want to show, but how you set up your image and where you take it and what compelling things you put in your image, that's the composition that Dale was talking about that you see in a lot of really good Milky Way images. You think about what you want your image to look like. And if you're going to use techniques such as, okay, the Milky Way is right over that tree or it's right over this rock, and you want to line it up and you want the sky and the ground. And when you do that, your sky and your ground connect. And now you're connecting planet Earth with the cosmos, with the Milky Way is what photographers call a leading line. So you're going to be drawn to seeing it, and you're going to be drawn into the surrounding area. And you're going to be drawn in, and you might even imagine that you're 150 million years ago, and those Allosaurus tracks just got laid down. You don't see any evidence of human civilization around. And you're going, this is what the sky may have looked like, except for the fact that most of this probably wasn't there. That ground had to have been there 150 million years ago, but all the other stuff there. You can imagine. Or just a simple rock formation, Milky Way, about a 20-second shot, I think. You go somewhere, you let the rock be the foreground. So when it comes to doing compositions of your Milky Way, get creative. What do you want to have that plays off of what's in the sky? And you can take a single shot and you can get it. There is some processing that's involved, but again, and I'll spill the beans. The darker the sky, the less concern with processing you'll have. So let's go. Yes.
Straight up out of the ground. That's because the pictures were taken from Texas, Oklahoma, that.
It's the time frame.
Where's north taking it? Start to flatten out for the horizon, isn't it?
They'll do the same thing no matter what. I've been to the Upper Peninsula, and unfortunately, I don't have the image I took, but I've got other images that are similar. Milky Way, depending on the month, you take your shot. So if you take your Milky Way shots as it's rising up out of the ground, it's going to be the same orientation, whether you're 43 or 44 north or 37 north. the further down you go, the more of the Scorpius arm you see as it's coming up. But the Milky Way moves very similar. If you're up here, you're only going to see so much as it comes up. If you're down here at 37, you see more. And if you're down even further, you see literally the whole arm. You see more of the whole arm up to a certain point. I've only been to 36, I believe. Yeah, the best I've seen is Omega Centauri. I've actually seen Omega Centauri, didn't realize Centaurus A was up there as well, but there was a full moon. So there are other things you can see besides the Milky Way, and the Milky Way will look a lot different. I will point some of that out because I was at Bryce Canyon in Utah, and we will discuss some of the things you may or may not see depending on where you are. So that was the secret, was dark skies. It just flat out, you want to take the best Milky Way photos ever. Photography wise, you can do things like stack images. You can run long exposures. You can get into a lot of processing theory, run noise exterminator, denoise software in order to get really, detail in the Milky Way. Your ground is going to be the same. It's depending on how long you want to image your ground, but the darker the skies, the more the Milky Way bleeds through. Here's a case in point. Remember that or you can see the skies. Let's just look at that dark sky map. The bright is only getting brighter with fewer places. The dark area west of the Mississippi, well west of it, it's pretty much, you get to Nebraska, the western edge of Nebraska, your skies start to change. You're going up in altitude as you drive further west. So not only are you getting darker, you're going higher up. Milky Way starts to show up a lot more. Where it says United States, something I think a little south of that is where the tip of Oklahoma is, where I took this picture. So you've got the picture of Port Crescent State Park, where you've got the comet here, and you've got this view of the Milky Way over the Pinnebog River. It's a beautiful image. Those were 2 minutes of exposure for the sky. And I forget how I did it, maybe a minute of image for the ground. That whole image on the right, where you see the Milky Way coming up out of this mesa, was a total of 11 seconds. Look at the similarities and how much detail I got in the Milky Way. Look at the difference in the sky color. This one I could have worked on. It looks a little more purple, and we see a lot more in the blue spectrum. This is what happens when you use a modified camera. That purple is evidence of a spectrum of red that we can't see, but it shows up in some of these. It makes this pinkish, whereas this was taken with a camera that was unmodified over here, over the mesa, and still some of that, a little bit of the hydrogen alpha light is still bleeding through even on that camera. Dark skies equals great Milky Way photos. It is the secret. Travel. And, whatever you put in front of your Milky Way photos, you can use rules of composition. You can do things like that. But the great secret is to look at that map of the United States, go to places that are dark, and take your smartphone out. If you have one of the later model smartphones, hold your smartphone for 10 seconds and you'll get a shot. Looks just like the one on the right. It's just that much more light coming down from our cosmos in those areas that are transparent, higher off the ground. Those are where the best Milky Way shots and any other type of imaging of the night sky you want to do are there. And I said, we have dark skies at the tip of the thumb. If you look at Michigan, you see we start getting dark skies when you get up here. You get away from some of the brightness down here. And then when you get into the Upper Peninsula, you see it's starting to get gray. The difference with our skies and the transparent skies here, we've got contrast issues due to our lakes, but you will still see a lot more in the upper reaches of our state than you will if you get down in here where we are right now. So that's the important key. The more, and you see up, if you get up to Canada, you know, those skies would be amazing. Now, how much to the south are you going to see? It's going to diminish with each line of latitude that you go. And it also, you have to think about your safety as well. You want to take the best Milky Way photos. And it may not be that you'll get attacked by animals or wayward people that are running meth shops out there. I haven't seen any of that. Your problem is not knowing the terrain and tripping, falling, hurting yourself, and no one's out there to hear you scream. So if you go, you must be careful when you get to a place that's dark enough. So take precautions, and especially with food. You have to take precautions with food because what's going to attract animals? Food. So eat before you go. All right, so the last couple, I don't know what I'm doing on time, but the last couple images I want to show, 2 images. This one I've taken recently. Focus is the final piece of a very good Milky Way photo. The more in focus you are, hyper focus on the stars at a lower aperture. So wide open, find a good, you know, between f2.8 and f4. Well, f1.4 and f4, find a good number that allows you to bring in as much brightness as possible and makes your stars as pinpoint as you can get them. And then some of the features and details will come out. Pay attention to this part of the Milky Way. This is Port Huron. This is Lake Huron. And there's Canada. I am on the side of the road at a roadside park in the thumb, right about here. Those of you can see. And Port Sanilac, Michigan. These skies are at around the 21.1, which is still very good for dark sky on a sky meter. You can get pretty good Milky Way detail. All the stars here. There's Sagittarius. There's the Scorpion. That's Messier 4. One of the little known things about good Milky Way photography is you start walking up and down the picture and you see DSOs that Jeff McLeod will be looking at through his telescope. He's looking at M4. Well, you can actually see the light from M4 there. M22, M8, there's M20. That's been a very popular region for astrophotographers because of the Vera Rubin images. M23, small Sagittarius star cloud, large Sagittarius star cloud in Body's window. This was a region that the arrow's pointing at near the center. It was pointing at. It was a region where exoplanet study was being done. The galactic center, right around here. That's where the center of our galaxy is. We call this the crazy horse. There's some dust lanes. There's Ophiuchus. For all you astrophotographers, there's a curious HA emission in Ophiuchus that looks like it comes in off of the galactic center. There's more dust lanes over here. Who knows, who's seen the wild duck in a telescope? The wild duck cluster M11. Ever wonder where it is in the sky. It's right there. That is where the wild duck is. And moving further, M26 isn't quite as visible. This constellation of Scutum is over here, and there's a ginormous star named VY Scuti that shows up if you magnify this. Go further, and you'll start seeing other neat and cool things. We miss Aquila in this shot because we chopped it off a little too much. So down here, you've got M6 and M7. You've got the butterfly Ptolemies. You've got the stingers, scorpion, and the lobster claw does not show up here. The cat's paw doesn't show up too well in this wide angle, but it's over here. And the rest of the scorpion, you see this going down. We just got the tail of the scorpion in this shot. Nothing that, and then there's the rest of the scorpion right here. So composition unintentionally wrapped the scorpion around the tree. But what does everyone look at? This water Milky Way. Whole lot more to a Milky Way shot than just the colors, composition. Even the sky color is intentional because the sky color changes when you go to a different area that's dark. So here's a quiz. I just named a lot of things. See if you can find them on the next image, which will be, I think, is my final one. Okay. Remember what we said about the Milky Way rising in the further south. This is Bryce Canyon, Yovimpa Point. All of a sudden, you can see the lobster claw and the cat's paw. All of a sudden, there's a lot more detail.
What state is this?
This is Utah, Southwest. So this is Bryce Canyon. It's its own little city. Which bright spot are we looking at? That's a town, distant town. Yeah, I don't know. We were debating that, looking it over at Yovimpa Point while we were getting our images. It's myself, Brian Ottom, and his friend Neil. And we said, what is that? And we figured it was just some distant town somewhere, but we never looked it up. So that's my homework, is to look that up. Notice a different orientation. This was taken earlier in the year, June, whereas I took that last picture in July and waited for the Milky Way to angle itself after moonset, and it got dark enough to take an image there. Here, look at the difference in the sky color. You can see the sky glow. We're seeing a little more now. Barnard Z is up here. I don't recall if the coat hanger made it into this image, but it's over there. Scutum is here, the shield. This part in Ophiuchus, because we cut the image off a little more. Now you can see more detail, the crazy horse. A lot of the dust lanes here were naked eye visible at this location. You saw this, you may not have seen it in quite the detail that you can see, that a picture will reveal, but these little trailing dust lanes, easily naked eye visible. Because sky glow, the camera picks it up. Green sky glow from radiation. So there's two things. There's aurora, which is the particles ejected from the sun interacting with our magnetosphere. This is the sun's radiation interacting with particles and causing them to glow. And when you take images lately, especially with an active sun, lately the sky glow has been showing up. It usually shows up in dark sites. Some of the images I've taken here in Michigan, depending on how deep an image you get, you can pick up that sky glow as well. So that green actually belongs there. There were a lot of Milky Way photographers that either tried to edit it out or they were confused. What is that? And we said, well, we're just now picking it up. The hardline astronomers that knew what it was basically told the rest of us, yep, that sky glow's there. It's for real. And because we're taking our images, we are picking it up and it's becoming a part of the images. So what you see, and this is where I open it up for question and answer. Best Milky Way photos ever are ones that you love, that you enjoy. If you're able to catch the Milky Way in detail over a beautiful landscape, even if there's a town in the way, or if it's just over a favorite place. Any image you come up with for your Milky Way shots. And it depends too on the orientation. Earlier in the spring, early summer, it's dark and the Milky Way is coming up, rising. And later on in September, where some of those other images, it's sunset and the Milky Way has already moved to a point where it's near standing up. As it goes throughout the year, the movement of the Milky Way will do this to where it flips over, the core will sink below horizon, and you have Cygnus resting on the horizon. On the other side, Cassiopeia, Perseus will be straight in the air, and coming down and rising will be the Orion Spur. You've got the galactic core, Sagittarius Rift, Sagittarius Arm. Cygnus is a part of that. Gets in through Lacerta to, let's see, Lacerta, I think, is in between Cygnus and Cassiopeia, or it's the other. I'll have to look it up. We are looking south. We are always looking south when we look at this part of the Milky Way where the core is. And we are, yeah, so south by southeast, because the Scorpion is sitting south. Cannonville? Okay, yep, small city, casting a light dome. It's interesting. Well, so you see this layer right here? That's smoke. There was a wildfire nearby. You see this haze? There's smoke. Yeah, your image. Now, if you want your image to be what you think it is, you're going to do a ton of processing. You can still get a beautiful image and just capture what you see, which is smoke from the wildfires getting up into our sky here. Sky opens up and all this becomes visible. And it is the difference between what you see in a dark place and what you see not so dark. The most striking example was seeing the Milky Way and seeing a level of detail that I didn't expect to see with a near quarter moon out. That was in Nebraska off of I-80 on the side of the road. I looked up, I saw structure. I detect color, but that could just be my brain. I could detect this full structure of the Milky Way as I was seeing with the moon behind me illuminating. I actually did take a picture of it, but I'll have to show you on my phone later some of the pictures that I took, other pictures I took on this trip. Yeah. Yeah.
Well, when we look at make it out of these, tiny spot out there, is that just the difference between a photograph and you make it ours?
So the question was, when we were up north, and we look up, we see essentially you see stars, we see it may kind of resemble a milk river, but you don't see the kind of detail that you're looking at in this picture. And is that just because it's a picture, or is the location so different that you actually see it like that in the sky? So the answer is yes, the picture brings out more detail than you can see naked eye, but what you can see naked eye in a place like here, a lot more of that structure becomes visible. The Milky Way becomes unmistakable. I would have to dull everything down, leave maybe a couple of the bright nebula here and the stars, and I would recreate what you would see. You would know it's there. It would not look like just a few stars here and some pinpricks. It would be very obvious. And that's not something anyone's used to seeing, especially in this area, which is why you go out west. That's why you can take a smartphone, hit the button, and get. Let me go back to that smartphone picture. Smartphone, because you see this dust lane. You see the crazy horse right there. You see these dark areas here where my arrow is, dust lanes. These are dust lanes. They're LDNs, large dark nebula. When the large dark nebula become visible, the Milky Way begins to take shape. And you look up and you go, oh, wow, there it is. And your eyes go from here all the way over to maybe you recognize Cassiopeia. Now, a lot of that is experience. When you first look at a really dark sky, you can barely make out any of the constellations. An image. Yeah. You do. Yeah, so, well, here's my question. Have you ever been to Utah or Colorado? Next time you go there, if you get a real clear night, even if there's a quarter moon up there, take a look up. With a quarter moon, it starts to fade, but it may still be unmistakable. Like you're saying, no moon, it hits you in the face, literally. You see, so winter Milky Way, one, you see it just as clearly. You don't see all the pink or the extra hydrogen emissions here. Right. Right. So yeah, and that's, you're talking about the bands. These are spiral arms that we're seeing from our vantage point. So this part of the spiral arm is a spur, the Orion spur, named because the constellation of Orion appears. That band appears here, looks kind of like, a lot of stars, because that's what it is. It's a density wave in our spiral galaxy. The other parts of the Milky Way are other density waves we're seeing through layers. Where the center is where all of that, the other picture at the end, that one we're seeing clear through to the large spiral arm aiming towards the center of the galaxy. Whereas on the outskirts, where the Perseus arm is, that's a different galactic arm that's in our field of view. They all link together to form our view of the Milky Way is actually a few a couple of different arms connected together. And it looks continuous, but if we were to leave the galaxy, and I know I have to get going, if we were to leave the galaxy somehow and look down, the whole shape would change. You'd see the center, but then you'd see these other arms at different distances because they are part of different arms. It's hard to describe that, and it's also hard to describe what you see when you go to even darker places, because it's somewhere in the middle. It's and I'll end on that note. What you see is somewhere in the middle of when you take a picture like this, where you've got a lot of detail pulled out of a camera, you still see some of that. It's unmistakable versus just being like a river of stars. And so there's kind of three ways to it. There's the image can pull this out. You got to get going. Yeah. All right. So thank you all. Yes. All right.
All right, so we're gonna take a 20-minute break? Yeah, take a 20-minute break. We're back at 8:20 and we will start our feature presentation. And it's not working. Wait, my mouse not working. All right, stop share.
Yes.
Thank you very much.
Okay.
I don't know, just a little mote of smoke. That used to be us.
She's online right now.
I want to find out. Family.
Yeah, I'm online. Did you want me to share my screen or you want to run them? I have a lot of clicks, so.
Wow, it's really loud here, Nancy.
Okay.
I have your presentation. Are you going to share it, or am I going to share it from this end?
I think it might be better if I could share
Okay,
it.
that's fine.
Okay, cool.
And I
Let me get
will-
it up then.
Let's see,
Bob, if you're talking to her, ask her if she's related to the Chabot family.
I am not related to the Chabot Observatory, so I wish I was in the Science Museum. They finally did invite me to at least give a talk there, which I had been waiting, many years for them to invite me to do, but no relation, unfortunately. It's a great place though.
I go to the observatory quite often, because my daughter is down the street.
come on up here, talk to her. Come on up here.
Yeah, come on and say hi.
Okay.
All right, let me share. Sorry, I got distracted.
Rid of that presentation.
Let me get rid of this. And go to here. I'm getting there. 1 minute. And
We need to allow you to share.
no, I think I have it. I just was trying to set my screens up the way that I like it. So
So I was rather surprised to see.
how does that look?
You're good.
Okay, great.
All right. So I was rather surprised to see that Dale got you as a speaker. I suggested him after you did that talk to the Vatican Observatory Foundation.
Yeah.
And he said, you see, our last meeting 2 weeks ago, he said you were going to be on. I'm like, wow, that's really cool. So, and I'm like absolutely thrilled that you're talking about the DART mission.
Oh, that's great.
The first lecture that I ever made was a lecture about meteorites, which quickly evolved into asteroids because I did that in 2013. And you know what happened in 2013?
I do. Yep.
Yeah, so I created a lecture on asteroids, and the problem with doing a lecture on asteroids is you need to update that a lot.
There is a lot going on. Yeah.
Oh my gosh, so much going on.
Yeah. No, there is so much going on constantly. So even this one, I updated this just yesterday, right? Before I'm giving this talk today.
The Hera mission into it.
Yeah, I had some of that Hera in there. I always pull, so there's one where you'll see I have the CNEOS, the JPL slide that shows like where all the latest fireballs are, and that gets updated regularly. And then of course there's 2024 YR4, so I wanted to make sure to put some stuff in about that, which was an exciting event.
I'll bet you can't wait for Vera Rubin to start finding stuff.
Well, I mean, that first light was already spectacular. They already found a ton of stuff, right? And that was just a test.
Scott Manley did a fantastic video shortly after those first videos came out, and he explained why DOD is in the name of it. I didn't realize that they were filtering all the data through them and taking the spy satellite stuff out. So yikes.
Yeah. Yeah, that's quite a pipeline that they had to work out in order to make it happen. But I mean, yeah, it's going to be a treasure trove of science. So many people are going to do so much with that data set, and it's just going to be available, and it's spectacular.
One of the things I covered at the very beginning was that new interstellar comet, and it's estimated that they're going to be finding a lot more of those things with Vera Rubin. And what was it? I heard that Vera Rubin is going to be generating more data than all of the other astronomical surveys combined. And the square kilometer array they're probably going to be competing with the amount of data. It's just amazing.
It is.
What an interesting time to be alive with all this stuff. I mean, child of the Apollo era, then to see, the first exoplanets and
well, I tuned in to see the presentation right before this, and that was spectacular too, right? I mean, and I just actually got one of these like small little digital telescopes, and it like works great as well, right? It's like super fun and easy, just
like what,
and yeah.
Oh my God.
So
a lot of Michigan astronomers swore up and down, left and right, they would never get one of those things, and they all have them now.
They're just just so easy, you know, for just kind of looking around and seeing things. And this was in my house. We only took it outside of my place in Arlington, Virginia, right? Like we just took it out on the front stoops. It's like light pollution everywhere. There's a used car lot across the street, you know, and yet, you know, so when he was saying like this is just with the phone, and then of course the other spectacular photography, but yeah, it's amazing the stuff that we can do these days.
I'm going to leave you for a few minutes here. I gotta go to the bathroom before we start
Yeah,
this up.
sounds good.
So I will be back in a few minutes.
Okay.
That's all prior to this training. Yeah, it's 16. I know, I remember I asked you about, he was your all-star first. That's who was. Yes. All right. Well, you saw my answer. I know they were. I know. Any else? I got that. A lot of this, at first, so I told you about my that was a nice guy. All right, that's okay. Yeah, I think I'll call What's up, Jerry? Actually, yeah, about 20. I just got back home. Yes. I'm super. Want to take it out of there? Okay, I just shot $20 from my hand. So. Okay. That photo I got. The only reason or super. You're getting down. I have
Okay, what time is it? 8:19, whoa. 2-minute warning. Get yourself a drink, finish up any bio, get yourself a munchie, and start the show in 2 minutes. 1 minute. Yeah. Let's see. I really wish we had a camera here for you so you could see the audience. I'll see if I can turn this around.
Well, I
Got it.
really wish I
Got
was
it.
there in person, actually, because it's always so nice to do these things in person, you know. But
You can see that.
it's a little blurry. Oh no, it's because the background's blurred.
Oh,
So I have to turn the background blurring off before I can see anything.
I really got to get a second camera and aim it back at the audience. All right, you ready to start? You can do this. Okay. All right, take your seats. Let's get this show on the road. I love this whistle. My wife got this at an antique store. It has the Thunderer on it, and it is just ear splitting.
Great.
She used it when she was a retired science teacher, and she used it in her classroom. Hey, sit down. We got a big crew here. Wow.
That's great.
The largest audience I've seen here in a while, actually. It's great.
Well, those photography was amazing.
Oh, thank you.
Let's see.
Thank you.
Yeah, she did. She did. He heard that. All right. The lights are down and now I can't see anything, of course. Lecture, geez. All righty. I have my eyes on. All right. Your last name is pronounced Chabot, right?
It is, yes.
Okay,
that's
good.
correct.
I hate getting last names wrong. All right. Dr. Nancy L. Chabot is chief scientist for the space exploration sector. She is the coordination lead on NASA's Double Asteroid Redirection Test, the DART mission, and she is the deputy principal investigator for the Mars Moon Exploration and Gamma Rays and Neutrons MEGANE instrument on JAXA, which is the Japanese Martian Moons Exploration MMX mission. She is an interdisciplinary scientist on the joint ESA-JAXA BepiColombo mission, which is going to Mercury. On NASA's Messenger mission, she was the instrument scientist for the Mercury Dual Imaging System and the chair of the Geology Discipline Group. She's been a member of 5 field teams with the Antarctic Search for Meteorites program. Oh, you've been to Antarctica. That's cool.
That's very
All
cool.
right, and she's going to be talking about the DART mission. So everyone, welcome Nancy Chabot.
Thank you. I assume that everything is good on your end. You can hear me and see everything just fine.
All right.
All right, great. Well, really happy to be here virtually. I guess, you know, it's always nice to be in person. Kind of wish I could actually be there in person, but to talk about DART, so the Double Asteroid Redirection Test Mission. This was the first mission to move an asteroid. So I am a firm believer that you cannot talk about the DART mission without starting on September 26th, 2022. Because this is indeed the day that humanity first deflected an asteroid. So broadcasting live from Johns Hopkins Applied Physics Lab, where I work, more than 1 million people watched this concurrently worldwide. That's the mission control, and we're closing in on these asteroids that have never been seen before, autonomously guiding itself, sending images back at the same time to Earth until the very last bit, and even just getting closer and closer, once image every second, and even just a little partial image until the spacecraft slammed into the asteroid. This had taken years to develop, to figure out the technology to make this happen. So lots of celebrations going on at APL, rightfully so, with the Mission Operations Center and all of the excitement that came with that. So we had a big party at APL and we were celebrating and we had done this and it was fabulous. But while we were doing that, Actually, LiCiACube was working. So the Light Italian CubeSat for imaging of asteroids was contributed by Italy, and it had been kicked off the DART spacecraft 14 days in advance, and it flew by the asteroids just a few minutes after DART had impacted them. So what you see are the asteroids here, and the one in the bottom right corner is the one that DART spacecraft crashed into, and this huge amount of dust and debris was ejected off as you do that. So it flew by and it turned around, and then it sees that. I'll let it play through one more time. So it's approaching here, taking these images, it's speeding on by, capturing this scene, this tiny little CubeSat from Italy, turns around once it makes its closest approach, and captures these images on the way out in order to reveal what happened, and then went on its way, speeding out of the system. These are the same images here that are stacked to keep the asteroid in the same place. So I'll play this a few times, but you can kind of see like the perspective of what you're actually looking at here then, where it's like a cone of ejecta. It makes a little bit more sense when you see it viewed in this sort of stacked configuration, where it's this one ejecta cone that's been coming out from that asteroid. But putting each image together, each image in itself has so much detail that was returned. And this one, for example, is just one of those LiCiACube images. But the contrast and brightness is stretched by a factor of 2 as you go out with each of those boxes, really to reveal the fine grain detail that you can see. And it's not a uniform amount of dust and debris going in everything, but there's streamers and there's complexities that have resulted because of this impact of the spacecraft. But it wasn't just DART that crashed into the asteroid and are celebrating. It wasn't just LiCiACube that got these images, but we actually had telescopes around the world on all 7 continents, literally on all 7 continents, and in space that were contributing as part of the DART investigation team to this there. Over 60 different telescopes are shown here on this map. And they were a critical part of the success of the DART mission and trying to understand what we did to the asteroid when we crashed into it.
My goodness, the VAT is on there.
I'm sorry, which one's on there?
The Vatican Advanced Technology Telescope in Arizona.
Well, there you go. So, and these are the ones who are on the team and contributed. There's actually more than this as well that have published data on them, and everything, but we don't want to take credit for other people's work. So these were ones that shared the data among the team with all of us, but it was a huge object, like I'll show you here in a second. So, and this wasn't coincidence. It wasn't just coincidence that all of these telescopes were there, because DART's timing for this mission was purposely chose to use these Earth-based telescopes. So DART launched in November of 2021 from the Earth. And there's the asteroid Didymos that it's going over towards. And, it journeyed for, a number of months here, as it got towards its target. And you can see the timing of DART's impact in September of 2022 was purposefully chosen so the distance between Earth and the asteroid was minimized. And so, at this point, it's, still, roughly 6 million miles away. So it's still like quite a good ways away from the Earth. But from the telescopes, they were able to get the best data that they've gotten in a long time. And this local minimum of the Earth and this asteroid lining up like this only happens roughly every 50 years. So really, September, the fall of 2022 was the right time to be able to do the DART test in order to take advantage of all the amazing telescopes that exist to capture the effects. And the telescopes did not disappoint, let me tell you that. So they got to work right away. So while we're celebrating in Maryland and in Italy, they're like working, to get the LiCiACube operations going. The telescopes in South Africa in particular were the ones that could look up at the night sky and capture the immediate effects of DART's impact. And so here you see this was captured from a telescope in South Africa, this immediate plume of material that comes off. And they were sharing this on social media as well. So while we're celebrating, we're like looking at the phones and we're watching these different movies come through each time. So really just a spectacular confirmation again from what we were seeing after the broadcast of NASA. About 5 hours after impact, both Hubble and JWST turned their sights towards the Didymos asteroid system and captured these images. This is the first time that both of these telescopes had looked at the same object at the same time. JWST had only been commissioned a few weeks prior to this, so this was some of the earliest observations of JWST. It was a challenging target for JWST, which is used to looking at things that are very far away. And this is a fast moving nearby object. So they really went to heroic lengths in order to enable these observations. But the DART impact comes from the upper left corner and is coming down, and you see this immediate cone of ejecta, sort of like you saw with the Lichia cube images. And then you're seeing this here in Hubble and JWST as well, 5 hours post impact. So many spectacular images, but jumping ahead a little bit, here's 2 days post-impact, and this is from a telescope in Chile. And DART, again, the impact is sort of coming from the left-hand side. You've got this diffuse initial cone of ejecta that's diffusing outwards, but by now, this cone of ejecta has also been pushed back into a tail due to the solar radiation pressure, very similar like you would have with comets. And forming this really long, spectacular tail. And telescopes around the world are just very easy to see this object, see this giant tail that's been forming. And this is a great animation that's put together from the VLT, the Very Large Telescope in Chile, that covers basically the first month of observation. So there's an immediate blightening of the system with DART's impact, a really wide ejecta cone that then evolves and gets pushed out into a tail of material that continues on here for the rest of the month. So brightening, ejecta cone, diffusing out into a really long tail of material. There's a lot of fascinating structure in there that was captured by the telescopes and how the ejecta is evolving in the system, and just a very rich and beautiful data set that was captured. Okay, but I could show images like this all night, and this audience probably that would go over really well. But jumping ahead even a little bit more, this is 53 days post impact now. 53 days. This is, nearly 2 months. This is from the Lowell Discovery Telescope in Arizona. And at this point, the tail is still super visible, really clear, measured at this point to be about 70,000 kilometers in length. Where is the end of the tail is a little bit of an esoteric sort of question, but at least that long, and just visible from these telescopes around the world. Jumping ahead again, 84 days post-impact, getting into the middle to late December here. Hubble Space Telescope again, this spectacular image, like showing a very clear, distinct tail with a lot of material in it. But what's remarkable about these observations are all those little blue dots. So if you see all those little blue dots, you might think, oh, those are some pretty stars that are also in the picture. Nope, those are boulders. Those are boulders that are 1 to 3 meters in size that have been also kicked off as part of the debris and the dust. And they've just barely escaped the asteroid system, and they're kind of trailing along in a similar trajectory around the sun. And there's just, tens of these boulders that are a meter size or bigger, that you can see spread all across the way. 169 days post-impact. We're in March of 2023. Lowell Discovery Telescope in Arizona. Again, tail is still very clearly visible. Every time that you look at it, there's got this clear tail of ejected material, even as we're getting nearly, more than 6 months post-impact. And then this is a stack of a number of Hubble Space Telescopes that were taken in, 9 months post-impact, 280 days post-impact, essentially in the June, July of 2023 timeframe. And still a really clear teal that you're seeing, but this is when the observations ended, right? Because now the geometry of the Earth and the asteroid system were no longer conducive. The asteroid had gone on to the other side of the sun, its distance had increased, and so we were not able to take any observations after this point. So when we left it in 2023, it had this really clear giant tail still, and then no more data for a while. And then in 2024, the observations were able to pick up this object again and continue. And this is some that were taken from a telescope in Chile. 615 days post-impact. And I've highlighted the asteroid there, but no sign of a tail. Since then, I've talked to a lot of other people who have observed this object as well, and nobody's seen any sign of a tail. So sometime between those 9 months post-impact and here more than a year later, it's the tail has ceased to exist. It's too bad we couldn't see it go away and see that whole process fully play out, but it's been a spectacular data set to use. As spectacular as the ejecta was, and as much as we learned from that alone and the evolution of that material and how those processes happen, that wasn't really the point of doing DART. The point of doing DART was to see how much crashing a spacecraft purposely into an asteroid could move that asteroid. And they were specifically using this Dimorphos system, the name of the mission, Double Asteroid Redirection Test Mission. And that's because this is a double asteroid system. There's Didymos, which is about 760 meters in diameter, and there's Dimorphos, about 150 meters in diameter. So Didymos was discovered by Earth-based telescopes in the 1990s, and it was known to have a moon that went around it. So hence Didymos in Greek means twin, because they knew that it was a double asteroid system. We got to help name Dimorphos before impact, and it was chosen to be Dimorphos because in Greek that means having two forms, because we knew it would have one form before DART's impact and one form after DART's impact. So the way the system works is that Dimorphos goes around Didymos, and we knew this from the Earth-based observations, every 11 hours and 55 minutes before DART's impact. This had been seen for decades. It had been very precisely measured that this was 11 hours and 55 minutes by those Earth-based telescopes. So the DART spacecraft comes in at 14,000 miles per hour, slams into Dimorphos. Lichia Cube goes by, takes those spectacular images that I showed you, and that impact of DART changes the orbit of Dimorphos around Didymos ever so slightly. And the telescopes get back to work to figure out how much did we deflect that asteroid. So the telescopes look at this system again, and they measure that now it takes Dimorphos 11 hours and 22 minutes to go around Didymos. So it's been changed by 33 minutes for its orbital period. Because this was a big change and we had so many telescopes and we had a lot of clear, beautiful nights, we were actually able to announce this just 15 days after the impact, much quicker than we thought. We thought we'd have to get telescope observations for at least a month, if not longer. But on just 15 days post-impact, we were very happy to have the NASA administrator himself run the press conference and say, today, NASA confirms that DART successfully changed the targeted asteroid's trajectory. Because we were able to measure that with the telescopes in order to demonstrate that success. So that measurement was made in two different ways. The first one is light curves, or sort of these occultation measurements that you guys are probably familiar with. And that's because as viewed from Earth, Dimorphos goes around Didymos, but sometimes Dimorphos is in the shadow of Didymos, so you get a dip in the brightness, or sometimes Dimorphos makes a little shadow on Didymos and there's a dip in the brightness, because as viewed from Earth, you can't actually see both asteroids with an optical telescope. All you see is a single point of light, but its brightness changes on a very regular pattern. And before DART's impact, this was 11 hours and 55 minutes. After DART's impact, it was 11 hours and 22 minutes. So this change of 33 minutes that the Earth-based telescopes were able to make, combining all of their data from all their different observations together to do this extremely precisely. The second way that we were able to measure how much we deflected the asteroid was actually using planetary radar. And so using the Goldstone in California and also Green Bank as well together, with radar, you can actually image the asteroids. So this is a radar image, and you can get data from both distinctly Didymos and Dimorphos. So Didymos is there from the radar return in this image, as seen in October. And you can also see directly Dimorphos in the image. And so you can get data from both of them independently. And where the position of Dimorphos is completely different in these radar images than where you would expect it to be with this 11-hour and 55-minute period. And when you take this into account, it's consistent with being this 33-minute orbital period change. So both the light curves and the radar gave us the same data in order to tell us how much we had changed the asteroid's path. So one of the main reasons for doing DART-2, though, was related to the ejecta, and that was because how much would doing this experiment on a natural asteroid actually move the asteroid? Because, you know, in the first case, if you don't have any ejecta, it's really just a very straightforward physics problem. The spacecraft comes in, it crashes into the asteroid, you know, and then that's sort of how it goes. And this is called like the momentum enhancement factor of 1, where basically what you bring in with the spacecraft is how much you push the asteroid, that's how much deflection you get. Nobody thought the asteroid would actually react that way. We all thought that, of course, you would have ejecta, and when you have the ejecta, it acts like a recoil effect. It actually helps push the asteroid even more because it's shooting the ejecta out in the opposite direction. And so like we saw in those images, there was actually quite a lot of ejecta. And so that helped enhance how much we were able to move the asteroid. So once you do some calculations and some other things, the best answer that we have at this moment is that DART momentum enhancement factor was actually about a factor of 2. What this means is that the ejecta like doubled the amount that we were able to move this asteroid relative to what you get with just bringing the spacecraft in alone. So this is a very promising result because the asteroid's kind of helping you to move it out of the way if you wanted to move it out of the way from, say, hitting the Earth in the future. This is the natural system, the natural behavior of the asteroid is enhancing the amount of momentum that you're getting, enhancing the amount of deflection. And this is also important because this is a good time to sort of explain how this whole kinetic impactor DART approach would work, is that this isn't something that you would do last minute. You would want to do this many years in advance, 5, 10, 15, 20 years in advance. And you would just give the asteroid a small nudge. And that little nudge wouldn't be enough to miss the Earth, but once it adds up over time, then you've moved it enough that the Earth and the asteroid are no longer on a collision course. And so here you might only need half the amount of time that you would need otherwise, is sort of what this result means. So along with seeing what we did to Dimorphos, we want to understand what does this mean for potentially applying this to other asteroids in the future if there was one that was on a course to threaten the Earth. So this is an example of a simulation that was done, taking the actual spacecraft model, crashing it into the actual topography that was determined from the images that I showed you to start with, and sort of seeing what would happen, you know, and this is the Dimorphos that was put into that model. And how the spacecraft then crashed right in between these boulders. And then this is an example of just one of the many, many simulations that was done. This one's at Lawrence Livermore National Lab from people on the team there. And what you can see is that, you know, you get this really wide cone of ejecta that's kind of splitting out from it. And if I just pause it in one of these and compare it to the Lichia cube images that I showed you to start with, you can see you're capturing a lot of the same features in these models. This very wide ejecta cone that's actually in streamers of material due to where it hit and which specific boulders it hit into, making that complexity that we saw so beautifully in those images to start with. This is another model then of what DART's impact did to Dimorphos with a hydrocode simulation where DART comes in, makes a wide cone of ejecta, spits material out. And the prediction from this one actually is that the shape of Dimorphos has changed by maybe as much as like 30%. It's the equator, the shape of it overall. So before DART's impact, if you were looking down on the asteroid, it might be more regular, like that blue circle. But then after that, it's actually has a slightly different shape than it did before. And there's some evidence in the observational data from the telescopes as well to suggest that this was true. So it was just a small nudge to the asteroid, but it might have actually resulted in changing its shape by up to 30%. And then there's the dynamics of the system, right? I mean, this asteroid used to be nice and happy, just going around every 11 hours and 55 minutes, but now we've put it into this new orbit, which is kind of messed up, whether it's tidally locked with only one face facing Didymos or whether it's there. So the best models of this, which I'll start here in a second, is that it's in a tumbling state now. So Dimorphos over there has the blue lines sticking out basically on like the XYZ axes. And before DART's impact, it would just sort of stay tidally locked, like the moon, always having the same face to the Earth. That's basically how Dimorphos was, we think, prior to DART's impact. And then this is sped up. So Didymos rotates every 2 hours and 2.26 hours. So you can see this is sped up quite a bit. But you can see also that those XYZ axes are not just staying nicely in place. They're flipping over. There's different sides facing Didymos. It's upside down now. So there's just a lot of dynamics that are going on in this system because of DART's impact. Now, I should say DART's impact was very safe. We just made Dimorphos even more tightly coupled to Didymos than it used to be. It orbits it even closer than it used to. So it's not like we knocked Dimorphos away from Didymos. Instead, we knocked it even closer. So there's no danger of it, spinning out and becoming a hazard. There was a lot of studies that were done as well that these ejecta are not coming to Earth anytime soon. So no danger from that as well. But the dynamics are really pretty fascinating here. But this is a good time to kind of take a step back and really address the question of, do we need something like DART? Why did we do DART in the first place? And this is a map that I just pulled down actually yesterday because it's updated very regularly at JPL on the CNEOS website. And these are fireballs reported by US government sensors for many of the last decades, since 1988. And you can see that the Earth is hit by objects all of the time. Probably a lot of people remember Chelyabinsk in 2013, captured spectacularly on dashboard cameras from a bunch of vehicles in Russia as it lit up the sky and eventually like impacted into a pond out there in Russia. That's one of the biggest ones that happened, but this really does happen all of the time. So to go more into it, a question I get a lot is, how often is Earth hit by asteroids? That question really doesn't make sense unless you talk about the size, because small stuff hits the top of the atmosphere all the time. Little dust is like burning up constantly, right? Something that's about 4 meters maybe hits about once per year, just to kind of anchor it on that end. A lot of these will not necessarily, they might burn up completely in the atmosphere. Maybe some of them will result in meteorites. I love meteorites. I study meteorites. I've been to Antarctica 5 times collecting meteorites. I was president of the Miracle Society. So I'm saying bring all the meteorites you want. So we should just let all the 4-meter objects hit. I love them. They're free samples from space. This is not the thing that we're concerned about. Now, Chelyabinsk is more like every 100 years. It was about 25 meters, a little less than 25 meters in size, actually. And it can cause an airburst explosion. And there were actually more than 1,000 people that were injured in the Chelyabinsk explosion, mostly from shattered windows. People would go to the windows, see what was going on, and then it would shatter. And so there were a lot of injuries, but there were no fatalities. There were no deaths. So you would want to have warning about this, but this is also not the priority for planetary defense at the moment. When people think about asteroids, they think about the dinosaurs and killing the dinosaurs. That's like 10 kilometers in size, roughly, for what people estimate for that one. The good news is that they're in the near-Earth object population. There are 4 of them. We have found all of them, and none of them are a threat to hit the Earth for the foreseeable future, which means in the next 100 years. So this is a very rare event. We're tracking all the objects that are this big, and none are a threat to hit the Earth for the foreseeable future. A kilometer is really concerning. A kilometer is about where people think that you might have, widespread devastation globally, because this would be big enough to potentially affect the climate, where you would start to change the climate of the planet, which would then have global effects rather than just being localized to the area that was actually hit by the asteroid. So this is a very real concern. This would be devastating for humanity. It's a very rare event, only about every 500,000 years. But there's also good news on this front too, and that is that there are about 900 of these. We have found 95% or more at this point. Of those, none are a threat to hit the Earth for the foreseeable future. We're tracking them, and again, there's no threat here. So This is always a concern, but it's kind of, we're tracking it, we know what we're dealing with. Which brings us to something more like the size of Dimorphos. 140 meters is chosen because that's where the US government says that you could have regional devastation, what they talk about, where the devastation could go out for 50 to 100 miles or more. And so it would be enough to potentially, if it hit over a heavily populated area, to wipe out a city, a small state, a small country, that kind of thing. So a huge amount of devastation if it was over a heavily populated area. Still pretty rare by the human time scale. It's about 20,000 years that something like this happens. There's about 25,000 of them in the near Earth object population. But the news is a little less rosy here because we actually have found less than 50% of this population that's out there. Now, of the ones that we have found, none are a threat to hit the Earth for the foreseeable future within the next 100 years. They're being tracked. People are watching where they are, but we actually don't know where more than 50% of this population is at this given moment. And something like DART requires on this advanced notice where you would be able to do something many years in advance in order to protect the planet. And just to kind of like what sort of devastation are you really talking about? Maybe some people in the room, or maybe a lot, have been to Barringer Crater, which is really close to the Grand Canyon out in Arizona. It's a beautifully preserved crater, highly recommended if you're out into that area. Just a spectacular, great visitor center. And it formed about 50,000 years ago by a 50-meter asteroid that was metal that hit. The crater that you can go see today is about 1 kilometer in diameter. But the devastation is much more than just what you see, that crater in the ground. When this thing hit, people estimate that the fireball would have gone out for 10 kilometers. And then you would have had large animals killed or wounded out for 24 kilometers and hurricane force winds out to 40 kilometers just from this 50-meter size metallic size object. So if you put this over someplace that's a little clear and dear to my heart, since I live out here in the DC area, again, you can see if it like bullseyes on a heavily populated area, just how devastating like this something would be. The entire fireball would take up the District of Columbia, and we'll just, no jokes about whether that's a good thing or a bad thing at the moment, but it would be bad for me personally. So this is why planetary defense is more than just crashing spacecraft into asteroid. It's got to be this coherent strategy that calls on a lot of different aspects. And search, detecting, and tracking and finding the asteroids is the foundation of planetary defense. You can't do anything about the asteroids if you don't know where they are. Characterizing them, what are they made out of? How strong are they? Is it one asteroid or two asteroids? That kind of thing. Or is also really crucial for helping you understand what you might do. Plan and coordinate is really interesting. There are United Nations level committees that actually discuss this topic with the Space Mission Planning Advisory Group and for the Emergency Response Working Group and also the International Asteroid Warning Network. Assess. You're constantly assessing the situation. That's where I pulled that fireball chart from CNEOS at JPL. And then there's mitigate, like if you need to do something about it, what would you do? And that's where DART came in as the first mission to demonstrate an asteroid deflection technology. There's also FEMA that's involved, running tabletop exercises. And this is all NASA's planetary defense strategy. It's really grown a lot in the years. NASA's Planetary Defense Coordination Office was only established in 2016. So this field has really taken off, and there's a lot of things that are continuing to evolve and advance in it. And it's not just NASA, it's actually in the United States, a whole of government there. There actually is a National Preparedness Strategy and Action Plan for the Near Earth Object Hazards and Planetary Defense from the Office of the President. And it has a very similar sort of goals that we were just talking about, detecting and tracking, modeling, doing something like DART for the reconnaissance, deflection, and disruption missions. I'm really encouraged all the time to see international cooperation as one of the 6 main goals of the United States strategy here. And then working across a lot of different agencies for goals 5 and 6. And down there's a whole alphabet soup of all the different agencies in the US government that have been involved in putting this strategy together. And it's not just US. So those were sort of the US ones with NASA and the national plan. But this is really a very international issue because asteroids hit everywhere on the Earth. And so this international cooperation for an international issue is really core to planetary defense. And it's really nice that DART intercepted the asteroid in 2022, but ESA, the European Space Agency, has already sent a mission, Hera, to rendezvous with these asteroids in 2026, but orbit with them, stay with them for an extended period of time. And from that, they'll be able to see what these asteroids look like, figure out the mass of Dimorphos, see if the shape of Dimorphos has changed, like we predict from those models that it doesn't look like it used to anymore. Hera is doing fabulously. It launched in October of 2024, and it's on its way to the Didymos Dimorphos system. It was a beautiful launch right before the hurricane came in Florida. I was lucky enough to be there. They've done a successful Mars flyby and captured some spectacular images on the way, so they are well on their way to do that. And it's talking about other future planetary defense exercises. You've got Hera that I was just talking about, but it's not just even that. There's also the Japanese mission, Hayabusa 2 Sharp, which is an extended mission of Hayabusa 2, which was a mission that brought back a sample from the asteroid Ryugu. And it's going to do a flyby of an asteroid that's about 500 meters in size next year. And then it's going to rendezvous with an asteroid that's only 30 meters in size with a 10-minute spin period in 2031. So that's very spectacular. China has announced that they are planning to do a mission like DART, but with 2 spacecraft. So one that would crash into the asteroid and one that would observe the effect, potentially with a launch in 2027 for that. NASA's big next planetary defense mission is called NEOSURVEYOR, which is an infrared space-based telescope, which is going to be capable of finding all of that 140-meter and larger population so that we will have that warning that we need and we'll know what we're dealing with. So this is a crucial foundation for planetary defense, and everybody's very excited about NEOSURVEYOR and the Rubin telescope as well, coming online in order to really give us much more knowledge about that population of small asteroids that might potentially threaten our planet someday. And then there's Apophis. So Apophis is scheduled to NASA's OSIRIS-REx mission. The extended mission would rendezvous with Apophis in 2029. ESA is looking at a mission called Ramses. JAXA the Japanese Space Agency is looking to send a mission called Destiny Plus, and other people are thinking about this too. And if you haven't heard about Apophis, so Apophis is this 340-meter asteroid, and on Friday the 13th in 2029, it's going to pass within some of the geostationary satellites, which are those little teal dots that you see going around there, through there. It's actually going to be a naked eye object across parts of Europe and Africa. And so you can look up at the night sky and see this asteroid. That is literally how close that it's coming. Now, we've been told that when we talk about Apophis, it's very important to stress that Apophis will not hit the Earth. Apophis will not hit the Earth. Apophis will not hit the Earth. It will not hit the Earth, but it's going to come really close. It's going to be spectacular. And people are excited to potentially send missions to it, as well as to all of the facilities, I think, and the telescopes will come back together and be looking this way as well for a really unique opportunity on Friday the 13th in 2029. Because of this, actually, the United Nations recently declared that 2029 is the International Year of Asteroid Awareness and Planetary Defense, to take advantage of the close approach Apophis and raise global awareness about asteroids. So the hype is already starting, and it's gonna, it's a thing to look forward to. Mark it on your calendars. So I've talked a lot about the asteroids that we pick, but there's a saying in planetary defense, actually, that, when it really comes to it, you don't pick the asteroid picks you. And that's true, right? We picked Didymos and Dimorphos because they were good targets for DART. We're picking to maybe go to Apophis with some missions, all the other missions that I showed you, but that's not actually the case that we have to be prepared for. We have to be prepared for the ones that pick us. So maybe some of you heard about this object here, which was discovered in December of 2024. It was called Asteroid 2024 YR4. It was first reported on the 27th of December. happens all of the time. There had already been like hundreds of asteroids that had been discovered in 2024. People are on holidays. This was like a total non-event when they found this thing. But as they kept observing it and getting more information about it, by January 27th, the impact probability had raised to 1% of potentially impacting the Earth in December of 2032. And so that's enough to trigger the International Asteroid Warning Network, who put out a thing nationwide to let people know that this might happen. And then the observations continued, and by February, it was up to a 2% chance of potentially hitting the Earth in 2032. And as of February, then, it actually rose to up to 3.1% of potentially hitting the Earth by mid-February, and people started to think about what sort of missions might we want to do to prevent this from happening. The estimates of the size were a little bit all over the place. We know now it's about a 60-meter size object because JWST looked at it since then. But then very quickly with follow-on observations, this object fell back down just a few days later to 0.3% and now 0.004% and then even lower after that. So we now know that this is not a threat to hit the Earth in 2032, which is good news because it is still a size that could do a lot of damage and that we would be concerned about. Last I checked, it does still have a 4.3% chance of hitting the moon. So that's still something that might happen in December of 2032. And we haven't been able to get more data on it yet because it's gone on to the other side of the sun. So JWST is taking some observations as it can, but just, that's how things work. You can't just always look at them whenever you want to. So this was a very real world example of exercising the International Asteroid Warning Network, dealing with an object that potentially was getting risen up to the scale that it could hit the Earth. Not, but it does show you that we really need to be getting ready as we just find more things with Rubin and with NEO Surveyor coming online. There will just be more and more examples like this. So taking a step back over to DART, DART really was an international team for this international issue. We had over 300 different scientists on the investigation team representing 29 different countries. And so we are really happy that we were able to maximize what we got from this project, not just from the telescopes, but from the modeling and everybody bringing their expertise to contribute to this global project that was DART. Because at the end of the day, this is all done by people. I can sit here and I can show all of this, but it's people coming together to do something that's bigger than any one person could accomplish on their own. And this is one of my favorite pictures of the DART spacecraft before it left our facility at APL in 2021. And it really gives you a sense of scale here with a person looking at it. And if you look at it this way, you can be like, this is the spacecraft that moved an asteroid. We built this, we put it together. We worked hard during COVID, actually. There were challenges, but this thing about the size of a person-sized spacecraft, we sent out on this mission to see if we could protect our planet from asteroids in the future. And it performed beautifully. So just to end, going back to where I started too, the spacecraft launched from Vandenberg Space Force Base on a Falcon 9. It went on its way. And here it was on July of 2022, 61 days pre-impact. And this was the first time the spacecraft was able to see the Didymos asteroid system. We had to stack a lot of images together in order for it to see it. And Didymos and Dimorphos were just a single point of light. But there you go. It's on its way. And this is the first time that it detected the asteroid system about 2 months prior to impact. And then here is what it looked like at 4 hours, at about roughly 4 hours prior to impact. And one thing I should mention is that at this point, it's going straight for the larger asteroid Didymos, because nobody's ever seen Dimorphos. We don't know what it looks like. And at this point, Dimorphos is basically right behind Didymos, so you can't even see it because it goes around every 11 hours and 55 minutes. So at this point, you're going straight towards the larger asteroid Didymos. The spacecraft had to autonomously distinguish between those asteroids, autonomously fire its thrusters to put it on a course to not hit Didymos, but to hit Dimorphos instead. And that whole thing was called SmartNav. the small body maneuvering autonomous real-time navigation system, and it turned on 4 hours and 5 minutes before DART's impact. So at this point, the autonomy took over on board, which people had spent a very long time developing and testing for the moment of truth. Would you be able to autonomously hit a small object in space going at high speed, 6 kilometers per second, that you've never seen before? This is when SmartNav first detected Dimorphos 73 minutes before DART's impact, and maybe you can make it out here depending on how the screen is. It's on the bottom right-hand sort of corner of there. Didymos is the bigger one, and Dimorphos off to the bottom right here. This is when it's first detected by SmartNav. And here, 50 minutes, just 50 minutes, less than 1 hour before impact is when SmartNav is very confident it knows which one Didymos is, which one Dimorphos is. It's firing its thrusters to autonomously change its course in order to start locking on to Dimorphos rather than Didymos. And this is that, again, last 5 minutes sped up here, where it's autonomously navigating itself. That's why it's jittery, because it's thrusting in order to not hit Didymos, to lock onto Dimorphos. All of that autonomy continues until the last 2.5 minutes. This image on board is being used for the autonomy, and they're also sending these images back 1 per second. Here at the last minute, you can finally see what this asteroid begins to look like. And really, it's only in these last tens of seconds that it really comes into view, hits the asteroid, sends this back, working until the very last moment. And that's a DART. So thank you very much. Super happy to answer any questions that you have, and thanks for your time.
Were you trying to hit it so that it would push it as much as you could closer, so that it would increase its orbit as much as possible?
Did you hear that, Nancy?
Not completely.
Could we repeat that? We were trying to hit it to move it as much as possible, or just to see what you could do with the impact?
Yeah, that's a good question. So we had a requirement that we had to move it at least 73 seconds, because that's sort of to get like a high precision measurement with the telescopes. We thought they would have a precision of like 7.3 seconds, and we wanted that to just be 10% of the overall detection. So anyways, this weird number of 73 seconds is like how much we had to move it by. If we hit it straight on and in the center, right, we always thought that it would be more like 10 minutes, you know. So then when it was 33 minutes, that was actually a lot bigger than we had necessarily predicted. That said, DART as a spacecraft was not as heavy as it could have been. We didn't make it try to go as fast as we possibly could, right? So, you know, if you wanted to impart more momentum, you would bring more mass and you would go faster. And we didn't try to necessarily do that. So we definitely tried to prove you could deflect it, but not like how much you could deflect it. A subtlety for that question is that now that we've done the models after the fact and how we saw Dimorphos reacted and how much ejecta there was, that some of the models suggest that even with the DART-sized spacecraft having the mass that it did, going the speed that it did, if Dimorphos had been 80 meters rather than 150 meters, we might have disrupted it, which is not deflection. It's like the opposite of deflection. It's breaking into many pieces, which is bad. You don't want to do that. Then you have lots of pieces to worry about. And so there's a fine line there between making it more massive and going faster might not actually help you if you actually disrupt the object and break it into a lot of pieces. So those are things that have to be weighed by future studies to take that into account.
They use an explosive device ever. Use an explosive device.
Would they use an explosive device?
Yeah, we'd like to not have to use an explosive device, right? So that's why we're trying. So DART made sense to do first because it's straightforward, right? You know, just crash some mass into an asteroid, kinetic impactor, no explosive devices. Just what you bring in is how much you impart with the momentum. You know, there are treaties that prohibit people putting nuclear devices in space. And so that is a good reason to, you know, that limits this as well. And there are a lot of good things about that outer space treaty. But if you were forced with an asteroid and you didn't have very much warning time, right, you know, and it was kind of upon you, you don't have a lot of very many good options left. You know, if you need something that is more push than you can get with just a massive spacecraft, then people have considered like what would an explosive device do. It's definitely sort of the last resort. That's why finding the asteroids is so important. So you have that warning time, so you can have a lot of good choices on the board. But if you don't have a lot of warning time, then your choices go down, and people have considered that. But there are also a lot of very real legal concerns.
Dale?
How did the debris pattern go from a splat to a tail?
Did you hear
Yeah,
how?
yeah, I heard that one. So that's the solar radiation pressure. So sort of just like the comets, when they get a tail, it gets pushed away, and it's a particle size sorting as well. So the smaller particles get like pushed faster earlier, and the bigger ones take a little bit longer. And that just kind of continually happens because of the solar radiation pressure.
All right, so let's solve it. My question is on detecting asteroids in general. Are we doing a better job of detecting them when they come at us directly from the sun as opposed to any other parts of the sky that we're able to see?
Not
There
the
are
sun.
limitations with the Earth-based telescopes in particular, right? I mean, so NEO Surveyor and getting up in space is really going to help a lot with sort of some of the fundamental limitations that you have when you're using Earth-based telescopes.
Question, did you say what the impact or speed was?
What was the impactor speed?
It was 6.1 kilometers per second, about 14,000 miles per hour, I think that is.
That's really going right fastball.
Yeah, it's going pretty fast, but that's kind of just the speed you get by like leading the Earth with the launch vehicle. So the speed that we got was mostly just from the launch vehicle. We didn't actually have a fancy spacecraft that like sped up or anything like that. It was mostly just what was came with the spacecraft ballistically to get off the Earth and get onto that orbit.
All right, no more questions? All right.
I
Thanks.
think there's one online, maybe from
there's
Greg.
one. I can't see that.
Well, he just says I have a question, so I
Yes,
don't know if he wants to
yes,
type it
I
or
do
talk.
have a
Oh, go
question.
ahead. Mhm.
Basically, I'm wondering, do you look at something like a physics terminology like the coefficient of restitution when two bodies impact? Is that part of the determination of what you should do? I mean, like for instance, if it's not a rigid body, say it's a rubble pile.
Yeah, it's
Would
rubble pile. Yeah, it seems like it.
would you want to do say a tractor, a vehicle that would follow the asteroid and nudge it gravitationally instead of impacting it? And if you want to do that, you really have to know what kind of asteroid is it? Is it rigid? Is it semi-rigid? Is it a rubble pile? That kind of thing. And how would you determine that?
Yeah, those are great questions. So there are kind of two flavors for planetary defense mitigation. There's the impulsive, which is like the kinetic impactor or the nuclear explosive device kind of thing, right? Where you do a one-time thing and you give it like a push. Um, then there's the ones that are called like slow pull or slow push, right? And so gravity tractor is actually one of those where you would go and you would fly a spacecraft and the mass of the spacecraft would slowly tug it like a tugboat and just like tug the asteroid out of the
Right.
way. And you would do this for years, right? You know, very slow, you know, decades of like tugging this asteroid. Another one that people like recently is called ion beam deflection. And so you'd again have an orbiting spacecraft with an ion engine. It just shoots its little ion engine like at the asteroid, which seems like it doesn't do anything. But if you do that actually repeatedly for decades, it does add up to enough of a force that you're slowly kind of moving this asteroid out of the way. What's nice about those is you have a lot of control, right? Like you're not making a lot of ejecta. It's very deterministic. You can turn it on and off. You're there with a spacecraft. You're watching the thing the whole time. The challenges are that you have to have a spacecraft doing this for like, 10, 20 years, right? Working successfully, so it's a, more of a challenge to do that. But people are very really working on those technologies, want to demonstrate them. DART was definitely just the start. It was done because it was the most mature, aka the most straightforward, aka the one that we're ready to test now. But people, especially the ion beam one, people are quite think there's a lot of possibilities there to orbit an asteroid for a long time and use the ion beams to slowly detect it. Like you said, it's going to depend on the mass, and it's going to depend on like how that mass is put together, but fundamentally on the mass, right? So how do you get that idea of whether it's like one coherent body or whether it's a rubble pile? If you're orbiting it, that's way easier to do. Like, so for DART, we didn't get a lot of information because you're just coming in at 6.1 kilometers per second and then you fly right into it. Or LiCube, right? Just flew right past, got some images. But if you're orbiting the body, then you can all of a sudden make much more sensitive measurements in order to get the mass of the body. And that's why Hera will be able to measure the mass of Dimorphos, for example, which is one of the main things that DART wasn't able to do. So from that, and you can even then get some higher order terms, potentially there's some instrumentation that maybe you could get to see, if it was a uniform density or whether it wasn't a uniform density. But if you really kind of understood the mass and you were doing one of these slow push, slow pull techniques, it probably wouldn't matter as much if it was a rubble pile or a coherent body. You just want to know how much mass you had to move in order to, make these things work. Now, if
Right.
you're worried about deflection versus disruption for your impulsive technique, this becomes even more important, though, whether it's a coherent body that's not going to break apart or whether it's a super weak body. I mean, Dimorphos seems like it was pretty weak, but we knew from OSIRIS-REx and the Hayabusa 2 missions, like Ryugu and Bennu, were potentially even weaker when they went to go sample those asteroids. Like they kept going in and in and in and getting the sample, and they had to fire the engines more than they thought. So, it might be pretty easy to disrupt some of these asteroids, and then you've just potentially made your problem a lot more challenging than it needs to be, where you've got a lot of objects coming at the Earth, not just one. So that I think that's where it becomes very important, like what you were saying, is how this thing is held together, what is its strength. So in planetary defense, what we've been advocating for as well is that really you'd want to do a recon mission. Like we went in there, we had never seen Dimorphos, we just went in, autonomy, identified it, hit it. Ideally, what you would want to do is you'd want to send at least a recon spacecraft, at least a recon flyby, see what you're dealing with, see if there's one or two objects, get some idea of whether it's covered with boulders or whether it looks like one big object. See if it's metallic or not. That would be huge because that's a huge difference in the amount of mass that you're dealing with. So ideally, it would be like discover it with the telescopes, send a quick rapid reconnaissance sort of mission, get that information, and then use that to maximize your mitigation.
Thanks.
Yeah.
Okay, any more questions? All right, thanks again, Nancy. And with that, our meeting is pretty much over. Our next meeting. Thanks, Nancy. That was awesome. Our next meeting is in 2 weeks, August 21st, Macomb Community College South Campus. Our next star party is Saturday the 23rd. That's also our picnic. Our next Cranbrook meeting here, remember, is September 8th. And several of us go to the Red Coat Tavern and indulge in gastronomy after astronomy. Woodward, north of 13 Mile. Join us there. Good night, everyone. Clear skies, safe travels. So Nancy, you still there? I have to tell you, on your asteroid lecture, when you're talking, you overlaid that blast pattern on DC. In my asteroid lecture, I overlaid the Tunguska blast pattern on Detroit.
Yeah, no, that's always kind of one of my colleagues, Andy Ripken, tends to put it over wherever he's talking at,
Yep.
so